Hello, Maria CBSE 2024 Warriors. Good morning, good morning, good morning. One of its class, one of its kind at 4 o'clock. Good morning for the final revision just on the day of your examination. For all the students who feel that they have not just done enough yet, or just need that motivation, or just need that last push or that last look at the formulas, but you're too scared to look at it yourself. You need someone to guide you and to revise it for you. Well, don't worry, your captain Shreyas Sir is just here for all of you, right? Welcome to the English channel, the #1 English channel in the country. Not just that, the favorite channel for your JEE NEET in your entire south and northeast as well as out of country. Thank you so much for joining in, and let's begin with the lecture. And good morning to all of you. So what I'm going to do in this particular session is quickly go through all the formulas as much as possible, and only the main important things from the entire of NCERT. We'll do it very rapidly so that we cover as much as possible in less amount of time, and many students can take the full benefit of this particular session. But before we do that, make sure you have smashed the like button and also hit the subscribe button if you have not done that yet. So let's begin with the lecture, my dear warriors. Okay, voice is cracking. Just a second. Just check it out now. Hello, is it fine now? Just check it out now. Hello, is it fine now? Why the hell did the voice crack up? One sec. Hello everyone, just check it out right now if it is fine. Just check it now. Is it fine? Hello everyone, just check it out right now if it is fine. Good morning everyone. Is it fine right now? Yes, it's fine. Okay, great. All right, let's do this then. Great, the voice is okay. So let's quickly start revising all the formulas, starting off with the first chapter, chapter 1, electric charges and fields. So if you go in this chapter, let's go to the important formulas directly. By the way, you should remember all the basic properties of the charges, the addition of charges. Q1 plus Q2 plus Q3 is the total charge. Charge is conserved. For an isolated system, charge before and charge later on is the same. Q is equal to NE. Again, a very important formula. N is the number of charges, E is the electron charge. Standard value is 1.6, 10 to the power minus 19 Coulomb. Okay, then going ahead, Coulomb's law, you should know the basic scalar form. K Q1 Q2 by R square. K is called as the Coulomb's constant, right? And the formula of the Coulomb's constant is, the value of the Coulomb's constant is 9 into 10 to the power 9. You should know all the constant values. Don't expect them to give it to you. You will also see the vector formula of it, which is 1 by 4 pi epsilon naught Q1 Q2 by R square into R cap. R cap is the position unit vector. Epsilon naught is the permittivity, whose value is 8.85 10 to the power minus 12, right? And it also follows Newton's third law. So F12 is F21. They are equal opposite, independent of the charges, right? Moving ahead to the next, Whenever there are multiple charges, what you do is take the force due to each of the charge and add them vectorially to find the net resultant force. That is the principle of superposition, right? You can have problems on triangle, square, hexagon, so much more. Electric field. Electric field is the force acting on a test positive charge, positive test charge, remember, right, per unit positive charge. So it is having the formula of 1 by 4 pi epsilon naught q by r square. If you want to write it in vector form, you put r hat over there. Okay, moving on ahead. Like I said, field is force per unit charge. That's why force is charge into the field. So that's alternative formula. Whenever you are given a charge in a field, you can find the force using this. Okay, moving ahead. Okay, all these things are fine. You should know the field due to a positive charge, negative charge. Due to positive charge, it is radially out. Due to negative charge, it is radially inside. And the field lines are always going to start from positive and end at a negative charge. Whenever you have multiple charges and you want to find the field due to that, you use superposition principle. You find the field due to each one of the charge and you find the vector resultant. Remember, field is a vector quantity. So you can see it is in bold. That means it is a vector quantity. Great. Moving ahead quickly to electric field lines. I just told you about it. Due to positive charge, it is outwards. Due to negative charge, it is inwards. And the field lines come close when it is stronger. It goes away when it is very, very weak. Okay. Whenever you take a surface and you see the field passing through it, you get a quantity called as a flux. Flux means flow. So flow of field is flux of electric field. As simple as that. And it is measured by, let me just come to it over here. Yes, it is measured by the field into the area into the cos theta is going to give you electric flux. The unit is Newton per coulomb into meter square. Newton per coulomb is field into meter square into cos theta. Theta is the angle between area vector and the field vector. Area vector is the vector perpendicular to the surface area. EA cos theta or EA dot A vector. Both are fine, right? Electric dipole is nothing but a positive and a negative charge together, and it produces a dipole moment which goes from negative to positive charge, and that creates also an electric field around it on the line of the dipole, that is called axis. Perpendicular to it is called as the equator. On the axis, the field is along the axis or along the dipole itself, and the formula for that is obtained. This derivation is important. We have done this. So on the axis, okay, this is given by 2qa. Okay, wherever it is finally written. Yeah, it is here. Yeah, on the axis it is 2p divided by 4 pi epsilon naught r cube. What is this p? Dipole moment. What is the value of it? Any one charge into the separation between the two charges. If it is separated by 3 meters, so 3 meters into any one charge, let's say 5 coulomb, will be the dipole moment. It is a vector quantity from minus to plus. So 2p by 4 pi epsilon naught r cube on the axis. Equator is perpendicular. So on the equator, it is against the dipole moment because the field lines go from positive and come back at negative. Start from positive and come back at negative. So on the equator, it is exactly opposite. It is p by 4 pi epsilon naught r cube. Remember, when there is minus sign, there is no 2 over there. When there is plus sign, there is 2 over there. That's how you remember it. Okay. And also keep in mind, it is not r square, it is r cube. It is r cube. I hope this is clear. Will I finish by 7 o'clock? I think I will try to finish it by 5:30 only, not more than that. Okay. So that after that, what you have to do, that also I will tell. At the end of this session, I will be telling you what exactly you should be doing. What exactly you should be doing just before the examination. This is very, very important. Keep this in mind. Okay. Sure. Let's move on to the next one. Come on guys, I want you to show full support and full josh and full energy, because yesterday also I took a long marathon. Before that I was driving. Before that also I again took session for you. Every day I've been staying awake. I think I have been studying more or almost just like you, just like I feel that it is my exam, because I'm doing this because I feel that it is for my students. So if the teacher only is not dedicated, then how will the students get that energy? So I want you to take that inspiration. I want you to think about all these things and prepare and give in your 100% for the examination. Okay, you are doing it. You are doing it to prove yourself. You are doing it for getting a good college. You are doing this to, have a very good percentage in your 12th exam, which will be there permanently with you as a mark sheet. Remember that. Okay. When you have a dipole in an electric field, it will experience a torque. The torque is P cross E. P is the dipole moment, E is the external field. The net force exerted on a dipole is always going to be 0. Net force on a dipole is always 0. Force is 0, torque is not. Then, when you talk about charge distributions and to find the fields, there are three distributions. One is charge per unit length, lambda, then charge per unit area, which is sigma, and charge per unit volume, which is nothing but rho. So rho, sigma, and lambda. Now you can see the different formulas also over here. So electric field, due to a uniformly distributed charge on a sphere, is given by this 1 by 4 pi epsilon naught, which is K, and then rho is density into volume divided by r square. This is r hat. It's a vector form. Don't worry about it. So just remember the formula in scalar form. That's enough. It's just kq by r square. So the uniformly distributed charge in space behaves like a point charge. That's what you can get to know from here. You can also see Gauss's law is basically a law which relates the flux through a closed surface and the total charge inside of it. The flux through a closed surface means you take a closed surface, you measure the field into area at every single point on that surface. You don't leave any part. Then you get the flux through the closed surface, and it always ends up being the charge enclosed by the permittivity. So Gauss law is true for any surface, no matter what the shape is. Q on the right hand side is only the inside charge, the total sum of the inside charge, and on the left hand side the field is due to both inside as well as outside charges. All these pointers which are there, okay, is very important. Gauss's law, although it is valid for any surface, you choose it in such a way that it is applicable for it becomes easier for symmetrical bodies like lines, surfaces, or spheres. So the calculation becomes easy. That's all. Otherwise, you can use it for anything. These cube problems, spherical problems, cylindrical problems are very, very common. You can see it's always been asked. Now the field due to an infinitely long wire, you should know the formula for it, and the final formula is 1 by 2 pi. It's not 4 pi, it's 1 by 2 pi epsilon naught r, and lambda, which is coulombs per meter. Charge per unit length is there on the numerator side. Next, due to an infinitely large sheet, because the field goes two ways, so 2 will come. So sigma by 2 epsilon naught. When it goes both the sides, 2 will come. Sigma is charge per unit area. When you talk about a shell, uniformly charged shell, then when you are inside of it, no matter where you are, enclosed charge is 0. So the field inside is going to be always 0. But when you are outside of it, then the entire shell collapses into a point charge, and you will use the formula for a point charge. kq by r square. K is 1 by 4 pi epsilon naught. So inside of it, it is always 0. For a uniformly distributed sphere, you will see that the field increases linearly till you reach the surface, and after you come outside, it behaves again like a point charge. So from center till the surface, it increases linearly. Okay, so that is a formula which is given over there. Alrighty, so let's move on to the next one coming up on your screen. The first one is done. Coming to the second one, just give me 1 second. Let me just drink some water. All right, let's go ahead. Nancy is asking, sir, explain the cube problem. So I'll tell you, in cube problems, there are mainly two variations. One is when at the center you place the charge. At the center of a cube, you place the charge. Then the flux will go up, down, front, back, left, right. It will be symmetrically distributed. Total flux coming out of the cube will be Q by epsilon naught. But if you take any one face, then 1/6 of the total flux will go through any of the face. So the flux through any one of the faces will be Q by 6 epsilon naught. That is when the charge is present at the center of the cube. Okay. Second variation is when the charge is at the corner of a cube. If you take it at a corner of a cube, you can imagine more cubes around it, and you can imagine in fact totally 8 cubes. And for all these 8 cubes, this charge will be at the corner. Think of a big cube of side length 2a. Instead of a, each cube of side length a. Imagine like that there are 4 below, 4 on the top. So totally 8 cubes. And for all the 8 cubes, this charge is going to be shared at the vertex or the corner. So you will see again, now it will get distributed symmetrically on the big faces. On the big faces of the big cube, the flux passing through will be Q by 6 epsilon naught. So if you want any one face, it will be 1/4 of that, because there are 4 cubes or 4 sides or 4 faces on each face, each big face. So 1/4 of that, which will be Q by 24 epsilon naught then. Okay, so that's how it works. So just imagine there are 2 cases and just replay this part, whatever I said again. The formula, the answer, I have mentioned it. Okay, cool. Then moving on to electrostatic capacitance and potential. Going over here, what are the formulas? Okay. Work done. Yes. Now, work done by a conservative force is negative change of the potential energy. Work done by a conservative force, yes, is the negative change by a of the potential energy, but the work done by the external force is without the negative sign, is just the delta U. So this is one important catch many students fail to realize. Conservative force is the electric field. So remember, work done by the electric field will be minus delta U, but some other person pushing it against that electric field, so that person's force is doing work, so that work externally is purely delta U without the minus sign. By the electric force, minus delta U. By the outside agent, plus delta U. Outside is plus delta U, internal, that conservative force will be minus delta U. That is what you should remember over here. And that is how you memorize the potential energy, and that's how you get the formula of potential energy, is the work done to bring a charge from infinity to that point. That is how electrical potential energy is defined, and the formula for that is KQ1Q2 divided by R. Similarly, you have potential. So work done per unit charge to bring it from infinity to that point is called as the electrical potential. So it is joules per coulomb, and that is volt. It's joules per coulomb, work done per unit charge. You can see right over here, infinity to the point. The definition is right over here. And the potential due to a point charge is KQ by small r, no r square over there. 1 by 4 pi epsilon naught is just K, Coulomb's constant. You can see the variation of potential graph and field graph due to a point charge is given. We had discussed whether it is hyperbola, parabola, etc. When it is 1 by r, which is right over here, 1 by r, it is a hyperbola. When it is 1 by r square, it is just a random curve. It is not a parabola or a hyperbola. Okay, I mentioned this in the graphical part session. Just check that out in case you haven't. How many of you have been keeping up with the 5-6 days challenge which I had started right from beginning? If you have, your marks are going to be like crazily amazing. And even if you joined in little late and you watched the recording, then also it's okay. Your marks will be much better than the situation where you had not watched any of these videos. Okay, is it clear? Yes, always for all of you, Navneet. No issues. Let's move on to the next one. All right. Now, the potential formula due to a dipole. Potential formula due to a dipole, just like you had field formula, it is K, which is 1 by 4 pi epsilon naught, P, which is dipole moment, which is charge into the separation, into cos theta. The cos theta is basically the cosine of the angle between the dipole and the position where you want to find the potential. This is the dipole moment. Here you want to find the potential, or here, or here, or here. So that is theta. So upon r square. Now please remember, when you are at 90 degree, that means equator here or here below, then the potential is 0. Keep that in mind. Okay, so that is what is mentioned right over there. Whenever you have multiple charges, to find the potential, you find the potential due to each one of them and you just add them. Some might be positive, some might be negative. Just keep into account the sign also. Don't make modulus. Okay, keep the sign also intact. And because it is scalar, you don't have to worry about the direction. Okay, so you don't have to do vector addition. Simple scalar addition is enough. Okay, those kind of questions. Where is the potential 0? Two charges are there, you find a point where potential is 0, or two charges are there, where is the field 0? These questions are also very, very common. Moving ahead, equipotential surfaces are those surfaces where the potential is constant, and due to uniform field, the equipotential surfaces are also parallel sheets, parallel planes. Due to a point charge, equipotential surfaces are spherical surfaces, and that to concentric spheres. Due to two positive charges, these are the equipotential surfaces. You should know that. Okay. Then also the relation of electric field is dV by dr. That means how quickly you change the potential decides how strong the field is, and the field always goes from high voltage to low voltage. That is why the minus sign, high to low, that means it drops. So field goes from high to low. So that's my minus dV by dl is your electric field strength. Whenever field is 0, that means dV by dr will be 0. That means voltage is constant. So whenever voltage is constant, then the field will not be there, because it does not have any place to go from low to high, high to low at all. So only when there is variation in the potential, only then the field will flow. When you talk about potential energy, I gave you the formula. It is K Q1 Q2 by R, not R square. Yeah, that is the potential energy. That is the energy required to assemble some charges together. Okay, all these things are fine. Now this is where you have more than two charges, some 4-5 charges are there. The total energy will be potential energy of each pair of the charges. 1 with 2, 2 with 3, 3 with 2, 3 with 1, 3 with 4, 4 with 1, all these combinations. So all the pairs, if you take 1 time each, you add their energies, you get the total energy of the system. That means the work done to assemble it. That is what the total energy of the system is. These kind of questions are common with squares, triangles, and so on and so forth. You should be aware of it. Energy of a single charge. Okay, one second, this is fine. This formula. Just like force is charge into field, same way energy is charge into potential. Okay, whatever is force, same way it is potential energy. Whatever is to field, same way it is to potential. Force is charge into field, potential energy is charge into potential. That's all. All right. You should also know the unit of electron volt. 1 electron volt is 1.6. Substitute the value of E basically. 1.6 10 to the power minus 19 joules. So that is something which you should be aware of, used in modern physics mainly. Okay. This and all is fine. Potential energy of a dipole in an external field. When you take a dipole and put it in an external field, it experiences torque, also experiences energy, and that energy is given by minus Pe cos theta. Minus Pe cos theta. So there is a minus sign here. I don't know why it went off. So it should be minus P dot E. So Pe cos theta is P dot E. P is the dipole moment, E is the external field. Keep this in mind. Also, you should know when the dipole is in the direction of the field, it is stable. When it is opposite, it is unstable. And when it is perpendicular, energy is 0. It is neither stable or unstable or neutral. It has maximum torque because sine 90 will be maximum. How many of you remember this, right? Then special conditions for conductors, electrostatics and conductors. Yeah, so Amodan, I just mentioned when is it stable and unstable. I hope you are listening to that. Great. Inside a conductor, electrostatic field is 0. Great. Yes, this is one of the very important thing. No field is there inside. Outside, it is basically perpendicular to the surface, and inside, because the field is zero, the potential is same everywhere. Keep that in mind. Potential is going to be there outside, definitely. Interior of a conductor can have no charge on it, so all the charges are always there on the surface, not on the inside part of the body of the conductor, like metals. See, we are not talking about rubber and insulators. Electric potential is constant throughout the volume because field is zero, so every point is at the same potential. When you are just going outside the conductor, the field is perpendicular and the value of the field is sigma by epsilon. There is no 2 here because the field is only going on one side. When you take a sheet, it goes on both, so 2 sides. Here it is one side, so sigma by 1 epsilon naught. That is how you remember this formula. Electrostatic shielding is where you are keeping a charge outside a conductor. The conductor will experience that field and it creates induced charges on it. But the charges align themselves in such a way that no field passes inside the conductor. So if you are inside, you will never know what was there outside. But the reverse does not hold true. If you are inside, if you have placed some charge inside the conductor, that field will eventually come out, not directly, indirectly, but by induced charges. So if you are placing a charge inside, you will experience a field outside. But if you are placing a charge outside, you will never experience a field inside. Point is, every time field inside is zero. Field inside is zero, field outside is going to be there. Okay. Then dielectrics and polarization. So dielectric is a medium where the medium gets polarized due to external field, thereby reducing the total field, and you reduce the field, reduce the force and all these effects. Okay. And this happens because of polarization. All right, all these things. You should know the polarization value. Its permittivity. Xg is a constant characteristic of dielectric. It is also known as electrical susceptibility, and E is the external field. So that is the polarization of any particular dipole. Its permittivity into Xg, which is basically your constant for your dielectric, also known as electrical susceptibility, like magnetic susceptibility, into the field. Now, the next thing that you have is capacitance and capacitors, which is a device used to store the charge in the form of on both the conductors, and the energy stored between those conductors in electrical form. And the capacitance is given by the charge stored upon the voltage difference between those two conductors. C is measured in farad. 1 farad is 1 coulomb per 1 volt. And then you have many different types of capacitances. One is the famous type, which is the parallel plate capacitor, where one is positive, one is negatively charged. There is distance, there is area of the plates, and there is field between them. The value of the field comes out as, this is very famous and very important, Q by A epsilon naught. Q by A epsilon naught. Yes, I'll be revising semiconductors also, Anush, don't worry. It's basically entire physics. It's basically entire physics of 12th standard. Correct. Q by A epsilon naught, that is the standard formula. From that, you get the value of the capacitance, which is epsilon naught A by D. Standard formula. Permittivity into area divided by the distance between the plates. That's what is given. When you add a dielectric medium, then what happens? The field tries to reduce. So to compensate that, excess charge comes on the capacitor to compensate for that loss and maintain the field. So the capacitance increases K times. The capacitance increases K times. The new capacitance is K times the old capacitance. The K is the not Coulomb's constant, it is the dielectric constant. You should know what will happen when you partially fill the capacitor with a dielectric medium. So each part will behave like a new capacitor in series, and you can use series formula to find the total capacitance. Okay. Now combination of capacitor, when you are in series, use the parallel formula. When you are in parallel, use the series formula. That's how simply it works. You can see it. This is for series, 1 by C1 plus 1 by C2 plus 1 by C3. When you are in parallel, you just add the capacitances, C1 plus C2 plus C3 and so on and so forth. Energy stored in the capacitor formula and the derivation, both important. Okay, the formula is half CV square or half QV or Q square by 2C. This energy is stored in electrical form. Keep this in mind. Okay, it is conservative in nature. When you divide this energy with the volume of the capacitor, you get the energy stored per unit volume, which is also called as electrical energy density. It is half permittivity into field square. Half permittivity into field square. Okay, so that's what is there in this particular chapter. Moving on to the third chapter. First formula is current, which is charge per unit time, right? Next is, I think current density will be there somewhere, or Ohm's law. Okay, yes. Ohm's law, voltage is directly proportional to current. Those devices are called ohmic devices. The resistance is voltage by current. You can use this formula even for non-ohmic devices, just that the resistance will keep changing for different voltages. Correct. Now, resistance is also given by rho L by A. Rho is called resistivity, L is the length, A is the area. Resistivity is a materialistic property. Resistance depends on the material and the length and the area. 1 by resistance is called conductance. 1 by resistivity, that means rho, is called as sigma, which is conductivity. Conductivity to resistivity, conductance to resistance, reciprocals of each other. Then you also have current density vector, I by A. I by A, current per unit area is also called as current density, J. So you will see that J into resistivity is equal to electric field. Why is there electric field inside the conductor? Because it is moving charges. In static charges, field is 0. In moving charges, obviously field must be there. So that field only creates the current to flow and the charges to flow. So just like voltage is current into resistance, instead of voltage, you use voltage per unit length, which is field, dV by dr is field. Current per unit area is current density. Rho is resistance per unit length, per unit area, and all of that. So that is the resistivity. It's like Ohm's law, but in a slightly different way. V is IR. So instead of voltage, you have field. Instead of current, you have density. Instead of resistance, you have resistivity. Okay. And like I told you before, 1 by resistivity is sigma, which is conductivity. All these electrons begin to move and they keep on drifting, and you have a drift velocity, the derivation again written down over here. And the drift velocity is E by m into tau. Tau is the relaxing time between successive collisions. You can also get current density is Ne square by m into relaxation time into electric field. That is also very easy to get. You can also see from this, you can also get conductivity formula, and that comes out to be Ne square by m into tau. Okay, Ne square into tau divided by the mass. Mobility is how mobile these electrons are, and it is the drift speed per unit field. Drift speed per unit field, that is the formula. Limitations of Ohm's law. It is not valid for many situations like semiconductors, where it is non-linear in nature. These graphs are very important. They might ask you, how does this graph look like for non-linear devices? Okay. Resistivity of various materials. So if it is a conductor, resistivity is less. If it is semiconductor, it is okay. If it is an insulator, it is very, very large. Resistivity also depends on temperature linearly. So it is rho naught 1 plus alpha delta T. Alpha is coefficient of thermal resistance. Usually the graph is straight line for a small range, but for a large range, it becomes a curved line like this or like this. And you can take a small part of it where it is linear, and only in that part you can apply this particular formula. Okay, so that kind of paragraph and question can also come. Why it is only applicable, how does the graph look like, and all of that. Okay, electrical energy, power. So whenever current passes through a resistor or a battery of voltage, we deliver some current. There is some power which is delivered, consumed, etc. That power is voltage into current, or V square by R or I squared R. All these formulas are equivalent for power. You multiply it with time, you get the energy, because power into time is energy or the heat. Then we go to EMF. EMF is basically electromotive force. It's the work done to move a unit charge once around the circuit. So work done per unit charge once around the circuit is called as the EMF. It's not a force, it's measured in volts. Volts is joules, the amount of energy, per coulomb, that is that charge which you are moving. So joules per coulomb is volt. Now, the voltage across a battery is never the EMF unless it is an open circuit. But usually when you are charging or discharging, the terminal voltage between the terminals of the battery is E minus IR when you are discharging. But when you are charging, it will become E plus IR. Keep that in mind. That's how it is. Okay. Then, when you want maximum current to be drawn from the battery, you do not connect any external resistance. So, the battery is said to be shorted. Maximum current will flow through the battery. So, it will be E by R. Okay. The current flowing will be E by R. That's the maximum value. When you want to connect batteries one after the other, it will be series combination. So, the EMFs will add, resistances will also add, just like for series resistances. But when they are in parallel, then the formula looks slightly different. It will be E1 by R1 by E2 by E1 by R1 plus E2 by R2 whole thing upon 1 by R1 plus 1 by R2. If there are more batteries in parallel, so it will be E1 by R1, E2 by R2, E3 by R3. You add all of them in the numerator. In the denominator, 1 by R1, 1 by R2, 1 by R3, 1 by R4, like that. And that will be the net EMF. Equivalent resistance of internal value, that is very simple. 1 by R1 plus 1 by R2 plus 1 by R3 will be 1 by R equivalent, the parallel formula. R, small r, is the internal resistance. Internal resistance is always there of the electrolyte. No matter what you do, it will be there. That will always cause some loss within the battery itself. For an ideal battery, small r is going to be 0. Kirchhoff's rules helps you solve complicated circuits. You have two rules. One is junction rule. So at any junction, current entering in is the current exiting out based on conservation of charge. Second is the loop rule, which is the total sum of the voltages across the circuit once is 0 based on energy conservation. You should know the signs. Whenever you go from small voltage to high voltage, it will be plus. Whenever you go from high voltage to low voltage, it will be minus. Like for capacitors, you go from minus plate to positive plate, it will be jump, so plus. Otherwise, from plus to minus will be a minus sign. For a resistor, you will always see, if you are going in the direction of the current, it will be minus IR. Against the direction of the current, it will be plus IR. For a battery, from negative to positive terminal will be plus E. For plus to minus terminal, it will be minus E. Keep this in mind. This formula, this particular problem of cube is very important. We have done this in the class. We have done this problem also in the class. Wheatstone's arrangement is this arrangement with 4 resistors. You connect a battery externally and you connect a device between these 2 points. If there is no current, no voltage between these 2 points, this bridge is said to be balanced, and it happens when R1 by R2 is R3 by R4, meaning this by this is this by this. Okay, so when that resistances are in the same ratio, then in between them no current will flow. That is called as balancing condition. Yeah, that is what is there here. Shall we go to the next chapter? Yes, formula for equivalent capacitance. I just told you, Srija, whenever it is series, you use parallel formula. Whenever it is parallel, you use series formula. Okay. Azwan, for derivations, just write only the main steps from my derivation session. Okay. Don't learn new derivations now. Now is not the time to learn new derivations. The old ones which you know, just practice the main steps on piece of paper. Don't see it. Just remember the diagram. Are you remembering the diagram? Just draw the diagram in rough. Quickly. It will not take you more than 2 to 3 minutes per derivation. You can divide the time now. After the session is over, next half an hour I am going to revise some 10 derivations. Easily possible. Okay. So do that. Just 1 second. Let me just drink some water. Come on, let's do this quickly. So, whenever a charge is kept in a field, it experiences a force of Q into E, but in magnetic field, it experiences a force of Q into V cross B. Together this force is called as the Lorentz force. One is the electrical part, one is the magnetic part. So QV cross B is the magnetic force. It's a cross product of velocity and magnetic field. So the direction of the motion of the charge matters a lot. Similarly, a wire carrying current has many charges moving under it. So because of which it experiences a force, and that force on a wire carrying current is IL cross B. You should know this. IL cross B. So there are some questions on that as well. So when you take a charge and throw it inside a magnetic field perpendicular to it, it goes in a circular path. This formula is very, very important of radius, which is mv by qb, and the frequency of angular is qb by m. qb by m independent of speed, independent of radius. But if you throw it at an angle, then it goes in a helical path, like a spring-like path with a certain pitch. Pitch is nothing but how much distance it covers per revolution. Okay, and that pitch is that velocity along the axis into the time period, into the time. So speed into time will be the distance which it travels in one time period. So that is 2 pi m by qb, which is the time period, into the velocity along the axis. You split the velocity into two components, one along the axis, one is perpendicular for the circular motion. 𝐕𝐞𝐝 law gives you the magnetic field at any point due to any current carrying element, like over here. I is the current, dl is the element, and that formula is mu naught by 4 pi, constant, which is 10 to the power minus 7. So it is ideal cross product with r vector, position vector, divided by r cube, that is the distance where you are measuring the field from the current element. That is your 𝐕𝐞𝐝 law, and this value is 10 to the power minus 7. To find the magnetic field due to the entire wire, you integrate the net field, you will get the answer. So this formula is also very important. A current carrying loop on the axis, what is the magnetic field going to be? It is mu naught by 4 pi. Where is it? That pi will also go off. Yeah. Okay. Mu naught I r square, mu naught current into r square radius square divided by 2, and whole thing r square plus x square whole raised to 3 by 2. When you put x as 0, that means you are at the center of the loop. So then it becomes mu naught I by 2r. There is no pi over here. This is how the magnetic field lines look like due to a loop carrying current. You should know it using right hand thumb rule. Okay, curl the fingers in the direction of the current, thumb points in the direction of the field. Then Ampere's law, which is just like Gauss law in electrostatics. Instead of electric, you have magnetic field. Instead of area, you have length. So if you go once around a loop, a path, imaginary path, just like an imaginary surface once, that's why closed integral. The value is permeability, mu naught, into the current which is passing within that loop. Current which is inside the loop is the enclosed current. Keep that in mind. Okay. Some important aspects related to Ampere's law is mentioned here. Just go through those 4 points later on. This you should know, this particular example, this solution, example 4.8, very, very important. So if you have a current carrying wire, inside it also there is field, outside it also there is field. So that is being derived using Ampere's law. You should know it. Inside it is proportional to r, outside it is 1 by r. This is straight line, this is hyperbola. So inside it is basically mu naught into current by 2 pi a square, a is the radius of the wire, into r. So that's why straight line. The moment you go outside, it is just mu naught I by 2 pi r. Small r is there below, so that is hyperbola. So you should know the graph, the formula, and the derivation. Solenoid is multiple coils, one after the other. So you have certain turns per unit length. Inside the solenoid, the field is roughly constant. At the ends, the field is slightly weaker, and completely outside, it is 0. Using Ampere's loop law, you can derive the field formula to be mu naught, permeability, n, number of turns per unit length, into the current. So that is the formula. Whenever you take two wires and place it parallel to each other, they might attract or repel depending on the direction. If it is same direction, then it will attract. If it is opposite direction, then it will repel. And the force formula you should know per unit length. It is mu naught I1 I2 by 2 pi d. F by L is mu naught I1 I2 by 2 pi d is the separation between them. If Force on one wire is this way, the force on other wire will be the other way by Newton's third law, action reaction. In fact, this is also used to define ampere as an unit. Okay, so current is a fundamental quantity, it is defined using this formula only. Then just like an electrical dipole experiences a torque, same way a magnetic dipole also experiences torque, and the formulas are very identical. So what is the magnetic dipole moment? Magnetic dipole moment, where is it? Yeah, magnetic dipole moment is basically you take a bar magnet or whatever, or an electromagnet, so those polarities create a dipole moment. It is given by the number of turns of the coil N into current which is passing through that coil into the area of the coil, NIA. So the torque, just like P cross E, will be M cross B. Instead of dipole moment electrically, there is magnetic moment. Instead of electric field, there is magnetic field. So magnetic moment is NIA, standard formula. Even energy is minus M dot B. So this derivation just says that an electromagnet behaves like a dipole. The formulas of the dipole are very identical, just like the electrical dipole formulas. So the field on the axis, field on the equator, all those formulas are similar. Wherever you see permeability, you replace with permittivity. Wherever you see electrical dipole moment, replace with magnetic moment. That's all. Everything else is same. That's what is mentioned in this entire paragraph. Moving coil galvanometer, the diagram, the derivation, and the sensitivity. All these formulas very important. And the deflection is proportional to the current. Deflection is proportional. How much it deflects is dependent on the current. It is NBA, basketball, NBA. Basketball you play in hand, but you do not kick it. Kick is there below your, yes, body. So it's below. So K for kick is in the denominator. Basketball in hand, kick below. That's it. That's how you remember it. And how to convert it into ammeter versus how to convert it into voltmeter. Both the variations you should know. Okay. So for ammeter, you apply a resistance in parallel called as shunt. To connect it into voltmeter, you connect a resistor in series. That's all that is there in this particular part. Moving on to the fifth chapter. Okay, a bar magnet, yes, is also is like a dipole. It has two polarities, north and south. Just the difference is that you can never separate those polarities. Like in electricity, positive and negative are separate. Here you cannot separate no matter how much you divide them. It continuous field lines which are there in magnetism. Okay, so bar magnet as an equivalent solenoid. Remember, these formulas are again getting repeated. Torque is M cross B, energy is minus M dot B. These formulas you have also seen in electrostatics. Okay, then all these formulas are just identical. There is nothing great over here. Directly go to Gauss law in magnetism. Just like you have electric field into area, the integration is charge in by epsilon naught. For magnetism, when you do magnetic field dot area for the entire surface, there is no net polarity inside, because whatever is north is the south polarity inside, because north and south cannot be separated. So no matter what surface you take, the total integration of the flux will always be 0. B dot A will always be 0 integration of it. That is Gauss law of magnetism. You can see it right over here. Okay, then you have the magnetic properties like magnetic moment per unit volume is called as the magnetization of the material. So if you take a material and if it is magnetized, that means the dipoles are aligned in a peculiar direction. So the magnetic dipole moment per unit volume is called as the magnetization of that material. Then if you have solenoid of certain turns whose magnetic field generated is mu naught Ni, then okay, it will create a magnetic field induced, yes, this one. The BM, the magnetic field which is contributed by the material placed inside external field, or the magnetic field which is induced inside the material, that is called BM, and it is mu naught into the magnetization. The H, magnetic intensity, is nothing but B by mu naught minus M. These are standard formulas which you should know. Don't remember this, remember this. This will be much easier than this. So the total magnetic field is permeability into magnetic intensity plus magnetization. H is called your magnetic intensity, remember that. The magnetization divided by magnetic intensity is given by susceptibility X, and relative permeability is 1 plus X. Relative permeability is 1 plus susceptibility. It is mentioned over here. Okay. Magnetic properties, dia, para, ferro. What is the range of susceptibility, permeability? You should know this table by heart. You should know how the materials behave in presence of external field. Dia will always repel. Dia is a common property by all the materials. Everything is diamagnetic. Paramagnetic is where they behave like temporary magnets. It will weakly attract the field. Ferromagnetic is because of domain formation, and it will strongly attract the field, and it is a permanent magnet. Also, the magnetic properties disappear after Curie temperature, and this becomes into a paramagnetic material after lot of heating. Keep this in mind. Okay, so if you are not so comfortable with these formulas, that's also okay. Some people always get confused between these things. If you have not studied it, it's okay, guys, leave it. It's of very, very low weightage. Don't worry about it. Okay, so don't get scared. Shall we go to the next one? All right, let's go to the next one. Electromagnetic induction coming up on your screen. Faraday's experiment, which shows how keeping the coil close or far away, changing the flux creates electricity, and the rate of change of flux is what gives you the EMF. So you have this magnetic flux through any surface which is not closed, obviously, because when you have a closed surface, the total flux is 0. It's an open surface, then the flux is B into A, or B dot A, whatever you want to call it. The EMF generated is the net rate of change of the flux with respect to time. So E is minus d phi by dt. Minus sign comes because of Lenz, who says that the EMF is always going to oppose the change in the flux. It is based on the conservation of energy. So if you try to increase the flux, the current will create a field to reduce the flux. If you try to decrease the flux, the current will try to increase the magnetic field in the direction of the flux. So it always opposes any kind of change. That is what Lenz's law is, and it is due to energy conservation, or else energy will magically increase or get destroyed. If you take a conductor and move it inside the magnetic field perpendicularly, the EMF generated is BLV across the ends. If the conductor is parallel and velocity is also in the field, then there is no EMF. Keep that in mind. Okay. Then, yeah, this problem is very important. You take a conductor and rotate it inside the magnetic field. Each part moves with different speed, so EMF in each part will be different. So the total EMF on the rod will be the integration of all of it, and it comes out as B omega r square divided by 2. B omega r square, omega is the angular speed, divided by 2. Then you have inductance, which is defined. Inductance is a property, it's a scalar quantity which is measured in Henry, and it tells you the electrical inertia to changes of current. So any changes of current, inductance is going to oppose it. So you should know the mutual inductance formula, self-inductance formula, and all of that. So mutual inductance of two concentric solenoids is mu naught, number of turns per unit length, in both the things, pi r1, that means the smaller coil, into the length of the solenoid. That is mutual inductance. You also have self-inductance, which is looking very similar to it. We'll come to that. Remember, EMF developed in one coil is mutual inductance of those coils into rate of change of current in the other coil. So that's why E1 is M di 2 by dt, and E2 will be minus M di 1 by dt. So current changes in one, EMF is produced in the other. That is mutual inductance. Self-inductance is where the EMF is generated in the coil itself due to the change in that coil. So E is minus L di by dt. L is self, M is mutual. Minus sign is because of Lenz. Okay. Self-inductance formula. mu into n square. Remember earlier it was n1 n2 for concentric. Now it is, instead of n1 n2, it's n square. Remember there was pi r square, which is area. So that is the area of the solenoid, and into the length of the solenoid. That's all. Okay. Energy stored inside an inductor is half Li square. Half Li square. Is the derivation of mutual inductance and self-inductance important? Yes, it is definitely important from the chapter of EMI. Definitely. It can come. Okay. It's a very straightforward. You can get it. Just somehow show the flux is proportional to the current. See, always keep in mind, phi, which is flux, is some inductance into current. So try to find the flux. How to find the flux? Field into area. Area, you know. Field, mu naught Ni. So derive it accordingly. You will see somehow flux will be something into I. Remove that I, remove that phi. Whatever is remaining is the inductance value. That's all. That's how you should derive it. Then this concept of AC generator and its derivation is very important. If you take flux as BA cos omega t, differentiate it, because d phi by dt is the flux rate of change, which is EMF. You will get the EMF, which is BA omega n sin omega t. So EMF generated by this method by rotating a coil is alternating in nature. AC current or voltages are developed exactly like this. This is a working principle of a AC generator. Okay. Alternating current, AC. So just like I told you, in AC the voltages are going to be varying, once plus, once minus, once this way, once that way. So it will be either sine or cos functions. So voltage is Vm sine omega t or Vm cos omega t. Vm is the maximum voltage or the amplitude of the voltage. Same way you can also write current is Im sine omega t, where Im is the maximum current or the peak current or the current amplitude. Omega is the angular frequency. How quickly is the current changing the direction is measured by omega. Current is voltage by resistance is only valid when the circuit only has resistance. Otherwise you cannot use it, because only when pure resistance is there, current and voltage are in sync, maximum, 0, minimum, in phase. Otherwise there is a phase difference between them. You also have a quantity called as the RMS value. RMS is that constant value which generates the same energy in that one cycle, okay, as that of the AC. So you can think it's basically, if AC voltage were to be converted into DC, what would that DC voltage be, so that same energy, same power is delivered. So that DC equivalent voltage for that power or energy is RMS, root mean square, which is maximum by root 2, which is maximum by root 2. 1 by root 2 is 0.707. That is some standard value which you should know. Now when you have AC voltage with the inductor, etc., then you will see the current and the voltages are not in sync. So when you take an inductor, the current is voltage by resistance of the inductor, called as the inductive reactance, which is XL. XL is omega L. And you will see that the current and the voltages are not in phase. In fact, you will see that the voltage and the current, alright, they are basically not in phase. Voltage is ahead of the current by 90 degree. Voltage is on the top, love is above all, L for inductance, L for love, love is above all, voltage is on the top, current is horizontal. So voltage is ahead of the current, keep that in mind. Okay, that's phase difference of 90 degree. When you have a capacitor, then again the current is voltage by the resistance of the capacitor, called as capacitive reactance. XC is 1 by omega C. XC is 1 by omega C, and exactly opposite over here, voltage across the capacitor below, current is here, current is ahead of the voltage for a capacitor by 90 degree. Now when you have LCR circuit, you take the vector addition of all of these voltages, vector addition of inductor, resistor, capacitor, you get the total voltage, and you get the total resistance of the circuit, which is called as the impedance. So it is R square plus XC minus XL whole square, whole thing under the root. Even if you put XL first, it won't matter, because anyways it is squared. You can find the phase difference, etc. Everything is vector addition over here. And remember, if you know vectors, you can treat voltages like vectors. The job is done. Okay, don't remember much formulas here. That's why I'm not doing it over here. So remember to use vectors. Love is above all, capacitor is below, resistance is here. So three vectors, you add them, you get everything. Resistance is here, XL is on the top, XC is here. You do the vector addition of the resistances, you get Z impedance. Now the current will change when you change omega, and for a particular omega the current is maximum. This graph is very important again. It's maximum at resonance, and the resonant frequency is 1 by root LC. 1 by root LC maximum current. The phase difference between the total voltage and the current is 0 because they will now be in sync. XL and XC values will cancel each other. The circuit will be purely resistive in nature. When you talk about the power in AC circuit, then it is voltage into current into cos phi. Okay, it is not just VI. Vrms into Irms into cos phi. This phi is the phase angle between voltage and current. Cos phi is called as the power factor. In resonance, power factor is 1 because phi is 0. When circuit is purely inductive or inductive or capacitive, then phi is 90 degree or minus 90. So cos 90 will be 0. So then it is said to be wattless because no energy is being delivered or consumed. Okay, so that is called as wattless. Wattless current can also come in your examination. In resonance, it is purely resistive, so only I squared R losses will occur purely. Okay, there is nothing else that can occur. Remember, inductor and capacitor cannot have any energy loss, they can only store the energy. Transformers are a device which is used to convert high to low or low to high voltage. Energy is still conserved, so when voltage increases, current decreases, and voltage decreases, current increases. It is based on the principle of mutual inductance. So current variations in one are transferred, and you will see voltage is induced in the secondary coil. And the formula for that is this one. V2 by V1 is N2 by N1. Voltage proportional to that number of turns. Current is inversely proportional. It's inversely proportional. So I1 by I2 is V2 by V1 is N2 by N1. Okay, that's a standard formula. So that's why I said when current increases, voltage decreases. There are three kinds of losses, and what you do for those minimization of the losses is mentioned right over here. So try to remember these losses and what is done. Okay, hysteresis loss, eddy loss, resistance of the windings, flux leakage. Okay, so all these points are important from theory point of view. You might get a question on that. So that was your transformers. Okay, sir, for mutual inductance mu naught N1 N2 A not divided by if you are using capital N, then it will be divided by length, but if you are using per unit length, then it will be into the length. Phasor for LCR circuit, Matidla, then I just told you, right? Love is above all, capacitors voltage is below, resistance is horizontal, and you take the vector addition of these three vectors to find it. Okay, that's all. Okay, is that all right? Yes. Yes, thank you for posting WP Krishna and Srinath. Thank you so much for giving that energy, giving that, support. We all need it. And everybody, let's gather all our strength. Don't get scared for any reason, because you might think, oh my god, this also I have to study, that also I have to study. Don't learn anything new. Whatever you know, just quickly mentally remember it. Just quickly revise it. That's why we are doing this session live over here for all of you, so that you can revise with me just before the exam, or else you might get tensed. Okay, all negative thoughts will come. Let's do this. What is this next chapter? Electromagnetic waves, displacement current. Okay, so first part is of Maxwell's equation and displacement current. So there are two kinds of current. Conduction current is the actual current. Displacement current is that current which is produced by changing electric field. and that displacement current is permittivity into rate of change of electric flux, d phi by dt, not of magnetism, it is by electric flux. So the equivalent current will be conduction current plus displacement current, that is the total current. So the Ampere's law will be modified to the B dot dl's total integration will be mu naught into total current, conduction plus displacement. That is the modified Ampere's law. And these Maxwell's equations are very important. This is your Gauss's law in electricity. This is Gauss's law in magnetism. Total flux is 0. Remember, because it is closed loops. This is your Faraday's law with Lenz's law, because E dot dl, field into length is the voltage. So voltage in a coil is the rate of change of magnetic flux with a negative sign. This is Ampere's law. So cyclic integral B dot dl is mu naught into total enclosed current. Take mu naught common, you will see it is the total current, conduction plus displacement. Electromagnetic waves derivation comes exactly through that. This is how electromagnetic wave looks like. So you have electric and magnetic fields perpendicular to the motion of the wave. Electric field equation, magnetic field equation is maximum field into sine or cos kx plus minus omega t. Kx plus minus omega t. Very good. Right. True Vision Media, thank you so much. When will the session get over? The session will get over in a very small amount of time, let me tell you. Okay, not much is left because modern physics and all these things are small parts. Let's do this. Come on, quickly. K is angular wave number 2 pi by lambda. Let's go ahead. Then speed of light is frequency into wavelength. Also, speed of light is electric field by magnetic field. Yes, speed of light is electric field by magnetic field. Yeah. So you can also use frequency into wavelength. You can also use this formula 1 by root permeability into permittivity. So if the medium changes, speed of light will also change. Moving on. Electromagnetic spectrum. You should know this chart properly with who comes first, who comes later on, and what are the different waves, where are they used, and what are their applications or their drawbacks, like are there any harmful effects, right from infrared, ultraviolet, radio waves, x-rays, gamma rays. Please remember this table, how it is produced, how it is detected, what is the range, etc. Okay, that table is very important. I will leave it up to you to revise quickly. Okay, moving on. Next, where did we go? So here first start off with your basic laws of reflection, incident rays, reflected ray, angle wise. Then you have focal length, formula for a curved mirror, which is the radius of curvature by 2, mirror equation, which is 1 by v plus 1 by u is equal to 1 by f, and its derivation. Okay, if you don't remember it, it's okay. Magnification is minus v by u. V is image distance, u is object distance, right? Then you have refraction, which is sine of I by sine of r is the refractive index. And here you get also, this is lambda 1 by lambda 2, which is also c1 by c2. Frequency does not change, please keep that in mind. The wavelength of the light changes when one medium changes. Okay, so that's why I said c1 by c2 and also lambda 1 by lambda 2. Also remember, refractive index of 1 with respect to 2 is refractive index of 2 with respect to 1, the reciprocal of it. So 1 mu 2 is reciprocal of 2 mu 1. Then total internal reflection, whenever light goes from dense to rare, chances of getting internally reflected are high, because if the refractant angle is more than 90, it cannot go into the other medium, it has to get reflected internally. Keep this in mind. Okay, and the critical angle after which the wave will get internally reflected is given by sine of I is 1 by refractive index, or refractive index is 1 by sine of the critical angle. You should know this. Okay, do you need to remember this table? Definitely not. Okay, what are the applications? You should know it. Optical fiber, all those things. Refraction at a spherical surface, that is a curved surface. The formula is mu 2 by v minus mu 1 by u is equal to mu 2 minus mu 1 divided by the radius of curvature. That's a standard formula. Then refraction by a lens. When you have two curved surfaces and you use the curved surface formula 2 times, you get the focal length of that lens, which is given by 1 by f is equal to mu minus 1 into 1 by r1 minus 1 by r2. This mu is the relative refractive index with respect to the outside medium. That is what is mentioned here. Okay, from this you get the lens formula. Instead of plus you have minus over here. So 1 by v minus 1 by u is 1 by f. It's very similar. There is no change there. Magnification, instead of minus v by u, here you have plus v by u. Power of a lens is basically 1 by f. For a mirror it is minus 1 by f. So signs are opposite, formulas are very identical. Okay. Remember, for a lens, focal length depends on the medium, but for a mirror, focal length is only dependent on the shape or the size, that is r by 2, that's all. It's not going to be dependent on the medium. When you have multiple lenses in contact, then you get the equivalent focal length like this. Take the reciprocal and add them like resistors in parallel. Basically the powers will get added, focal lengths never get added. That's the combination of lenses. But if you talk about the magnification, each lens might produce a magnification m1, m2, m3. You multiply them, you get the total magnification. Okay, right. Thank you, Madida. Yeah. Oh, Syed Aryan, I'm so glad you are back to see me and say hello to the students, your juniors. Yes. Thank you, Krishna. Thank you, Krishna, so much. Moving on. Then prism and its derivation. See, in ray optics, if you are not able to remember the derivations of lens formula, etc., at least remember prism's derivation. Second is lens maker formula's derivation. Okay, it is very important. It might come. R1 plus R2, that is the internal angles. R1 plus R2 is A, that is one thing. And also the deviation produced is I1 plus I2, which is incident plus emergent, minus angle of the prism. You should know this. The deviation changes with incident angle. It is minimum when incident angle and the emergent angles are equal. R1 will be equal to R2, and you get the refractive index as sine of A plus delta by 2 upon sine of A by 2. That's the formula. Microscope, you should know the ray diagram and its derivation. Alright, so the magnification due to a simple microscope for least distance of distinct vision is 1 plus d by f. If you are using it for normal vision, meaning the image is produced very far away, then instead of 1 plus d by f, it is purely d by f. D is 25 centimeters. D is 25 centimeters. This is the least distance. Know the ray diagram for a compound microscope when you have two lenses together. Okay, so the distance between the lenses is called as the length of the tube of the microscope. Objective is the one which is closer to the object. Eyepiece is the one closer to the eye. Both have their own focal lengths. The formula is very important. Finally, what you get, magnifying power, is length of the tube by focal length of the objective into distance of least vision upon the focal length of the eyepiece. That's the standard formula. For telescope, it is focal length of the objective by focal length of the eyepiece. The only difference is, for a telescope, the object is not close by, the object is very far, so the object is at infinity. So the rays are almost parallel, so they converge at the focal length, and then you again make a real image back over here. And the length of the tube is f0 plus fe. That's also a standard result. Okay, nothing more over here. Moving on. Come on guys, last 4-5 chapters remaining. Let's do this really quick. Within no time, you have revised most of the things. Yes, it's 5:30. Let's try to cover everything as much as possible in the next 15-20 minutes with me, my dear students. Let's move on. Wave optics. Huygens principle and Huygens construction, very important. To prove refraction and reflection, also very important in Huygens principle. They are very easy also. It's not that difficult. Okay. Then I've done those derivations. If you want, you can watch them for your last minute revision. This coherent and incoherent sources. Coherent means the sources are in sync, maintaining a phase difference. Incoherent means they are random. So any two random light bulbs will be incoherent in nature. When you derive two sources from the same source, like you create two slits, then those two slits will behave like coherent derived sources. The path difference plays an important role whether to see whether they are going to interfere constructively or destructively. So yeah, over here you will see that the intensity of the resultant wave when they interfere is given by 4 I0 cos square phi by 2. I0 is the intensity due to any one wave. Phi is basically the phase difference. Phi is basically the phase difference between the two waves meeting at a point. Phase difference is 2 pi by wavelength into path difference. 2 pi by wavelength into path difference. What is path difference? One wave is traveling this much, one wave is traveling only this much. So the difference of their paths is called as the path difference. That's all it is. This is your Young's double slit experiment, the famous setup. You should know the diagram, okay, and how the fringe pattern occurs, which is alternate bright and dark bands. And you should know the position for the maxima or the bright fringes, which is n lambda d by d, and for the dark fringes, which is n plus half into lambda d by small d. N plus half because it comes out as odd number. The fringe width is lambda d by d. The fringe width is getting affected when you immerse the setup in a liquid, because when you immerse it in a liquid, the refractive index will change the wavelength, thereby changing the fringe width, which is lambda d capital divided by small d. Diffraction is the phenomena where the light spreads when it passes through a hole or an aperture. The single slit setup is very important. If you can remember the derivation, good, nothing like it, but if you can't, that's also okay, not so important. Hopefully it doesn't come, but still, okay, you can just go through it once. So you will see that even through a single slit, you get alternate maxima and minima. The difference is that the intensities are not consistent. In YDAC, every bright dark has the same, levels of intensity. But in diffraction, the first 0th bright is very bright. The first bright is little bit dim. Then the next maxima or the next bright is even faint. So it becomes, fainter and fainter as you go away, and it disappears after 2-3 maximas. That's the major difference. You can take two blades, keep them very close, pass the light through it. You will see a diffraction pattern even at home. Okay. And then you have polarization, which is only observed in transverse waves like light and wave on a string. Sound is a longitudinal, it will not show polarization. So the plane of oscillation of a wave, when it is, in a peculiar direction, the wave is said to be polarized. But if it is having oscillations in all possible directions, then it is said to be unpolarized. The light from the sun is unpolarized because it will emit light waves in bursts in random directions. So the electric field will be once vibrating like this, once like this, once like this, once like this. So it is said to be unpolarized. When it passes through a polarizer, which is a special crystal or liquid, then some components are completely cut, only a certain component is passed, then the light becomes polarized in nature. If you use another polarizer after it, and if it is exactly aligned with it, all the light will pass through. But if it is perpendicular, then that light will also completely get eliminated if it is perpendicular. Okay, so you should know about this, and you should also know Malu's law, just in case. Okay, I'm not sure if it is here. Yeah, it is right over here. I is equal to I0 cos square theta, meaning if I0 is the intensity of the light falling on the polarizer, then if the polarizer's angle and the light's oscillation angle are aligned, then the complete intensity will come out. But if it is at an angle, then that means the polarizer, it has an angle with the angle of the oscillation of the light, then a smaller intensity of light will come out. The intensity which comes out is incident intensity into cos square theta. Theta is the angle between the polarizer's plane and the light's oscillating plane. Keep that in mind. If it is perpendicular, like I said, nothing will come out. Oh, by the way, if it is unpolarized, then the intensity which comes out is I0 by 2. I0 by 2. Okay, just hold on. Vision 720 after some time. All right. Cool boys, very cool. Your 11th standard paper is there and you are coming and attending 12th standard. Very good. But yeah, I think you should watch my older classes. Right now 12th standard is very, very important for everyone. Okay, not like 11th is not important. It's just that, you know, students in 12th become very serious, very tensed for small things. So I need to be there. Next year I'll be there for you. So don't worry, watch my older classes. You will be able to understand everything, and very soon we'll be starting off with 11th standard classes on this particular channel. Okay, whatever chapters are remaining, we'll be doing it. Okay, don't worry. Okay, going off to dual nature, what are the important formulas? Okay, these statements are very important over here. What are the different ways you can emit electrons? Thermionic emission, field emission, and photoelectric emission. What are these things? And you should know it. So going ahead, photoelectric effect, the experimental setup is there. Okay, the graph is there of photocurrent versus the voltage. How voltage to stop it is independent of intensity is there. Okay, saturation current, you should show it. How intensity is proportional to the current, that also is an important graph. Then maximum energy of an electron which is emitted is charge into the stopping voltage, another important formula. How frequency of the light affects the current, that is also a very important thing, and frequency decides the stopping voltage. It's not dependent on the intensity. Stopping voltage versus frequency graph is standard slope. Slope is h by e. It's independent of the light or the material. The material decides whether the graph will shift here or there. Okay, so this graph is also very, very important. Yeah, photoelectric equation. This equation you should know. Maximum kinetic energy, remember it was E into V0, which is stopping potential, is HF, that is the energy of a photon, minus phi naught. What is phi naught? Work function. What is work function? The minimum energy to suck out that electron out of it. It is also HF naught, F naught being the threshold frequency for the photoelectric effect to occur. Okay, phi naught or phi is basically work function. So phi is HF naught, that F naught is nothing but the critical frequency after which the photoelectric effect will occur. Keep this in mind. Then the particle wave duality, you should know. Wave nature of matter, yes. So if you have a particle of momentum p, then the wavelength associated of the matter wave is h by p. Even p, momentum of a photon, is h by lambda. Lambda is the wavelength of the light. Both relationships hold true. Okay, that is all that is there formula wise in this chapter. Moving on to the next one, that is the fourth one over here. Yep. Quickly, in atoms, what are the different formulas that you have? First of all, you should know all the theories: Rutherford's theory, the gold foil scattering experiment, okay, and also the scattering angle versus, you know, the number of particles scattered, the least distance of approach. These concepts may come. How the electric force provides the necessary centripetal force for the electron to revolve in circular orbits, and that is used for derivation. So how, you know, close particles to the nucleus get completely rebound, and as you go away you will see the scattering angle reduces, so the closest distance of approach also will change right over here. Electron orbits, okay, this is fine. I think we have come to Bohr. Did we come to Bohr? Where did Bohr go? So Bohr's model. Before that only they have given over here the radius of the orbit and all of that. Yeah, so radius of the orbit is proportional to n square by z, velocity is proportional to z by n, and electron's energy in any orbit is proportional to z square by n square with a negative sign. And remember, energy is minus 13.6 electron volt, z square on the top, n square below. Okay, these derivations very important. If you know it, very good. Then we'll talk about the series also, Lyman-Balmer-Paschen, we'll come to it. And before that, the Bohr's postulates, you should know all the three postulates. The first postulate is of the orbits, stable orbits. Second postulate is angular momentum is principal quantum number into Planck's constant divided by 2 pi. And the third postulate is the energy difference between two orbits is exactly the energy of the photon which is absorbed or released. If a photon is absorbed, electron will get excited. If an electron is de-excited, photon, light will come out of it. That is very, very crucial. And these are the different energy levels. Remember these values, draw this graph if a question comes on the energy levels of hydrogen atom or explain the energy spectrum. You should know these things, how the energy initially is very low, it's negative because it is bounded. As you go up, energy increases for higher orbits, but the lines come closer and closer, and finally they are very, very close, and then you get zero energy level. That means the electron will be completely free. Okay. Then the de Broglie's explanation of Bohr's second postulate of quantization. This diagram is very important. You can see there is a standing wave like structure formed over here. So exactly wavelengths are being included in the circumference of the orbit of the electron. So lambda, how many times? N times. N is principal quantum number, is 2 pi r. So 2 pi r is circumference, is lambda into n. That is what de Broglie said. That is what de Broglie said. So this formula is also very, very important. Moving on. Next one, to nucleus. Yes, one atomic mass unit, you should know the formula. It's 1/12 the carbon 12 isotope, 1.66 10 to the power minus 27 kg. Standard things, mass of proton, mass of neutron roughly the same. Mass of electron is very, very small. Okay, discovery of neutron by Chadwick. Then you have atomic mass number is the total number of protons plus the total number of neutrons inside the nucleus. The size of the nucleus formula is R0 a raised to 1 by 3. R0 is a constant which is 1.2 femtometer, which is 10 to the power minus 15, also called as Fermi. A is the atomic mass number. When you divide the mass of any nucleus by its volume you can find by 4 by 3 pi r cube, you will see it comes out to be constant, and the order is 10 to the power 17 kg, 10 to the power 17 kg, which is huge. Einstein said when you destroy mass, energy is created. When you create mass, energy is destroyed. Okay. Victor Pandu marriage with Natalia at 10:30. Who is this? Victor, your board exam is there and you are thinking of marriage. Either you are not a 12th standard student, or if you are a 12th standard student, then you are very genius. You are ultra pro max legend. Please concentrate on the class. E is equal to mc square. M is the mass, c is the speed of light. Okay, by the way, you can also write energy in terms of mass defect in electron volt. So energy which is released or absorbed is mass defect, or the mass which is destroyed or created, into 931 mega electron volt. That is a more useful formula. So you get this thing called as binding energy. Why binding energy is important is because whenever you assemble the protons and neutrons in a nucleus, some of the mass gets lost in terms of energy. So that mass lost is mass defect, which is the mass of individual protons and neutrons minus the mass of the nucleus. That is mass defect. You put it here, you get energy as mass defect into c square, which is 931 mega electron volt into the mass defect in AMU. Always mass defect in AMU when you are using 931. When you find the energy for binding it per nucleon, that means the number of protons and neutrons together, you divide it, then the graph looks something like this. This graph, very important. This shows the stability of the nucleus. This being more stable, this being less stable, this also being decently stable or not so stable as iron. These people want to break down into small parts by fission to become more stable. These people want to fuse together to become more stable like iron. This graph tells you the stability because more the energy being released per nuclear particle, that means it is coming to a lower energy state. Lower energy state means more stability. That is why this graph is related to stability. Nuclear force, this graph very important. It shows that for very small distances, you will see that the energy is very low. As you go even few femtometers, immediately the energy goes up, or when you come very close also, again the energy goes up. So the nuclear forces are very strong for few femto or Fermi meters. Okay, this graph shows that. And this force is independent of charge, independent of mass. It's a new force in nature like electric, magnetic and gravitational forces. And also remember, it acts for a very short range and it is the strongest force in nature. Radioactivity, you should know about alpha, beta, gamma decay. Alpha is doubly ionized helium. They are very heavy, bulky particles, slow moving. Beta is little bit tiny. They are electrons with one single negative charge. They move slightly faster. Gamma is nothing but a photon just in that electromagnetic spectrum. They are the fastest because they move at speed of light, and they are the most energetic and highly penetrating in nature. Okay, right. So fission and fusion processes, you can just remember few examples. Don't have to remember all the reactions. Just remember one of these and you can give it as an example to explain fusion and fission process. Okay, don't have to remember all these things. They are just given for all of you. Controlled and uncontrolled fusion fission reactions, I doubt they will ask, but even if they ask, try to leave it as an option because not much is given over here. It's more of history or general knowledge kind of paragraph which is given over here. Okay, so don't waste your time much over there. In semiconductors, what are the different formulas that we have? You should know resistivity is 1 by conductivity. You should know the approximate range of resistivity just in case. Okay, then the examples of semiconductors: elemental type silicon and germanium, compound type CDS, GS, CDSE. Okay, these are compound type. That means two elements combined together to form a compound and they behave like a semiconductor. Okay, then on the basis of energy bands, you should know how the energy band structure looks like for conductors, insulators and semiconductors. For conductors, they will overlap, conduction band and valence band. For insulators, the band gap energy is much more than 3 electron volt. If it is less than 3 electron volt, few electron volts here and there, then it is a semiconductor. So electrons can easily jump from valence to the conduction band. Intrinsic semiconductor is where it is completely pure, no adulteration, no doping happens. It's having equal holes and equal electrons. These electron and hole pairs are formed due to thermal collisions. So when atoms collide, electrons are ejected out. A vacancy is created which is positive, which is like positive, and it is called as a hole. These electrons keep moving freely. The electrons moving this side and that side are equal. The holes moving this side and that side are also equal. So there is no net current in an intrinsic semiconductor. The value of the holes or the electrons per unit volume in an intrinsic semiconductor is called Ni, which is also called as the intrinsic concentration, intrinsic carrier concentration. When you add some impurity onto it, then you are going to add basically the impurity. So you are going to add either holes or electrons in excess. Otherwise, you will see the holes and the electrons concentration is equal. And whenever you apply some battery's voltage, even the electrons move and even the holes will move. So the current in a semiconductor is due to both electrons as well as holes. Whereas in a conductor, it's only because of electrons. There is no positive charge moving. That's one major difference. Okay, keep this in mind between semiconductor and conductor. Also remember, a semiconductor is an insulator at 0 Kelvin, because at 0 Kelvin, no energy is there thermally to excite those electrons from valence to conduction band. So all the electrons are in the valence band. So there is a gap. So that gap can't be overcome because there is no thermal energy. So semiconductor turns into insulator at extremely low temperatures. Keep this in mind. Extrinsic is when you add these adulterations. So when you add an excess electron with a pentavalent extra electron, pentavalent impurity, then it becomes N type of semiconductor. Okay, so that is N type. So electron concentration is more than hole concentration. P type is when you add trivalent impurity, which creates a vacancy that makes an additional hole. So holes concentration is more than the electron concentration. That also improves the conductivity. Remember, for P type or N type, the product of hole and electron concentration is Ni, which is intrinsic concentrations square. A p-n junction is where you add p and n type material, sandwich it together, you get a depletion layer because the electrons diffuse into the p type material, creating a no man's land, like a dead zone, called as the depletion layer. It also creates a wall of potential called as a potential barrier. The electrons going to the p type creates the diffusion current. Same time, there is opposite current which is established called as the drift current, which happens because of thermal energy. Okay, keep this in mind. Now this is barrier potential. You should be able to draw all of these things. Okay, now a p-n junction is also a diode. Diode is a device which allows current in one direction and blocks the current in the other direction. So why does it happen? Because of this potential barrier which is created. So if the current has to be established in the forward bias, it is very easy, because once that potential barrier goes down in forward bias, sudden surge of current comes, and that barrier potential, once it is overcome for that surge, that voltage is also called as the knee voltage. For germanium it is, I think, 0.3, and for silicon it is 0.7 volts. In the reverse bias, this barrier potential becomes even higher, so it becomes even more difficult for the electrons or the current to be established. So you will see hardly any current flows, and that current in reverse bias is also called as the leakage current, also expressed in this particular graph over here. Forward bias, sudden surge that happens after new voltage. In reverse bias, you will see hardly any current is there. Yeah, but after a point, you will see there is a sudden increase of the current in reverse bias. That is called as the breakdown. So breakdown occurs after a certain voltage is applied, and you will see the voltage does not increase after a certain point. It remains constant. In fact, this is the principle used in a Zener diode to regulate the voltage. So Zener diode is again used in reverse bias. You should know about resistance versus dynamic resistance. See, in this current versus voltage graph, if you measure the current and you measure the voltage and divide it, you will get the resistance. Resistance here will be different because it is a non-ohmic device. Resistance won't remain constant. There is another quantity called as delta V by delta I, rate of change of voltage with respect to current. That is not resistance, that is called dynamic resistance. So if they ask you dynamic resistance, find the change in current, change in voltage, divide them, you will get dynamic resistance. Okay, keep this in mind. Another application of diodes is in rectification, where you convert AC voltage into DC. Two ways are there. One is half wave, where the complete wave's half part gets converted into DC. So that is half wave rectifier using a single diode. You should know the diagram. Then using a center tap transformer using two diodes, you get full wave rectifier. So the positive and negative cycles both are converted into DC voltage. So you will see the entire AC voltage is converted into a DC voltage. So you are using the full wave, that's why a full wave rectifier. Usually these variations are too much. So to remove those variations, you filter it out and you make it almost constant by applying a capacitor in parallel to the output, which can store and give the charge when required, thereby stabilizing the voltage. So a capacitor is used to stabilize the voltage. Great. So this is also done now. Perfect. So I think we have revised as much as possible in this last 1 hour 45 minutes. Now, capacitor filter vector, it's basically the capacitor stores the charge. Let's say the voltage is too much. Okay, it stores, thereby reducing that current and the voltage. Okay, it does not allow it to go too much. And when the current or the voltage drops, then the stored energy is given into the circuit back, thereby maintaining the voltage. That's how it is able to maintain constant voltage. Otherwise, the output is maximum minimum. Very uneven voltage and current is there. It is not uniform. A DC should be flat. It should not be varying. Okay, because a DC which you expect from a battery is a flat voltage. I hope that is clear. Now, what you should do right now, is basically whatever things you might have seen that, oh, I need to see this, see that, that's all. Don't read anything new. If you want to see the derivations, you can go through it, but I would advise to practice it on a piece of paper for the next half an hour, not more than that. Any formula that you want to revise again, write it and revise it and do it randomly. Don't learn new formulas right now. Don't learn new derivations right now. Don't learn new chapters right now. Okay, then 1 hour before the exam, stop everything. At least 1 to 2 hours. You should peace out, calm down. Don't call anyone. Don't talk to anyone who is going to be very negative. Eat proper breakfast. If you did not have enough sleep, if you can manage to sleep for some time, sleep, because you need to keep your mind active. Also keep in mind your time. Divide time properly. If you have given mock test, you know where you consume more time and where you consume less time. Try to be as quick as possible, but do not spoil your handwriting for that, and do not be very slow and improve your handwriting but you are not able to complete the paper. Please keep in mind, if whatever is the paper duration, leave at least 20 minutes for the paper verification, or 15 minutes at least. Okay, keep a target of T minus 15. So try to complete the paper 15 minutes before. Only then you will be able to solve all the questions. In the last 15 minutes, you can verify the calculations, underline few things. Also remember, sometimes you might think to underline something, and when you put the scale or whatever, your ink will get distributed. So don't do it immediately. So do the underlining part later on. That's okay. It's not like after the question I want to underline. Then you'll be wasting a lot of time. Okay. And what happens is, in the end, if you underline, it will be also like re-verifying the answers. Always box the result. Don't solve the questions in random order. Go in the specific order. It is easy on the mind for the examiner. Okay. And don't solve the problems in two sections. So if this is a page, don't solve half the problem here, half the problem here. Continue. Don't try to save pages and all of that. Okay. And don't write unnecessary stories. Stick to the point. If there are 3 points, write 3 points. If there are 2 points, write those 2 points. Don't make up your own points. Don't unnecessarily repeat the points in different words. Examiner will easily catch you. You will lose marks. Also remember, there is step marking. So if there are 2 questions, both are in options, and you don't know both of them completely, think which problem, which question you know better. So you will get more step marking for that. Okay. So if both questions you don't know, see which one you know better and solve that part. All right. Don't solve both and give the examiner only an option. Don't do that. Okay. That won't work. Also, bear in mind to solve each and every question. I have seen many times students forget to solve one sub part of the question. So check each and every question sub part if you have solved it. Sometimes you might lose 1 or 2 marks because you have not solved some part of the question. Okay. And see if you understood the question properly. Sometimes the examiner is asking something, you write the answer only for something else, because you see that the question is familiar and you had got this during the pre-boards, but maybe what they have asked is slightly different. So be calm. The first 5 minutes is a confidence booster. Take some time to settle down. After 5 minutes, you will go with the flow. If you want, don't look at the entire paper, just go with the flow systematically. Question 1, 2, 3. Don't even look at the papers completely. Okay, that might unnecessarily cause a lot of tension in your minds. Is that right? Okay. Have you smashed the like button already or not? Have you subscribed to the channel already or not? Do that, because your next preparation is going to begin after the physics examination. I'm not going to spare you. Don't relax. It's not a time to relax after physics exam. Your captain Shreyas Sir is going to be here. And yes, support the channel, talk about the channel. When you visit the exam center and you saw some question, tell that, yeah, Shreyas Sir was teaching this and this came. This question I learned in this session. This graph came from this session. I will be very happy when more and more students join and get benefited from this particular channel. Thank you so much. All the best. Shreyas Sir and the entire team wishes you all the best. May the paper be exactly what you imagined it to be. Maybe the questions are exactly what you have seen and which you are familiar with. And may everything what you have studied, be recollected by all of you, and you are able to complete the paper on time and let the paper go very, very smoothly. Those are my wishes to all my lovely students. God bless you all. Take care. Hasta la vista. Captain Shreyas signing off.